Great.
Good afternoon.
Ladies and gentlemen.
Yes, ladies and gentlemen, good afternoon. At this part of the symposium, I am going to switch for English because now we have all the speakers are going to give their talk in English. Therefore, I will conduct the introduction and the questions and answers in English. But please don't be afraid. You can ask your questions in Portuguese, and then somebody translate for us, and then we can give help with the answers. I have a great pleasure right now to continue our symposium and invite Dr. Marek Gizonika. I don't know if I pronounce it correctly. So he's a professor at UK at the Cambridge University, and he is going to give us a talk named Intracranial Pressure is More Than the Number. Dr. Marek, it is a great pleasure having you here this afternoon, and please, you can perform your presentation. Many thanks.
Thank you. Thank you. Thank you. Thank you for inviting me to be with you, with Professor Mascarenhas. We all know his insightful and smiling eyes. Professor Mascarenhas was a great friend of our little laboratory in Cambridge. It's called Brain Physics Laboratory. And in his memory, the best thing that would be to talk about intracranial pressure. I'm sure he would be enjoying this little contribution. Intracranial pressure is more than a number. And that has been the first time shown by French scientists, Julien and Jenny, and then further, almost 10 years later, by Professor Niels Lundberg in Lund. He was lucky because he published his research about intracranial pressure monitoring in English. The previous works of Julien and Gianni were not that well noticed because they were published in French. Professor Lundberg, Gianni, and Julien showed that intracranial pressure may be very much variable if we monitor this in time. So this is really more than a number. One events may show us the normal pressure, and 5 minutes later, pressure really elevated around 50, 60 millimeter of mercury. These are plateau waves of intracranial pressure. And these are also very high, of high dynamics, B waves of intracranial pressure as described by Lundberg. At the foundation of intracranial pressure, we believe there is a Monroe-Kelly doctrine, stating, and that has been formulated later after Monroe and Kelly by Professor Cushing, that volume of the brain, volume of cerebrospinal fluid, and volume of the blood in a closed skull must remain constant. That's got a great consequences on intracranial pressure, because intracranial pressure is therefore the function of 4 components. This is arterial blood inflow, venous blood outflow, cerebrospinal fluid circulation, and volumetric changes of the brain tissue. That's got really very important consequences of how we control intracranial pressure. We need to know which of these components should be altered to bring elevated intracranial pressure back to the normals. For example, if this is alteration of blood inflow, vasoconstriction. If this is alteration of venous blood outflow, number of measures like head elevation in patients after traumatic brain injury, thrombolysis, or in chronic states like idiopathic intracranial hypertension with venous stenting. If there is a problem with CSF circulation acutely, we need to apply extraventricular drainage to improve CSF circulation, or once again, in chronic cases like hydrocephalus, we need to think about shunting of the patients. If this is a problem of a brain volume, we need to apply osmotherapy. We need to apply the principles of Lund protocol, surgery to evacuate the lesion, or decompression. All these four mechanisms can be illustrated in clinical practice, and I will show you these four cases. First of all, this is alteration of the arterial inflow. This is plateau wave of intracranial pressure. When intracranial pressure increases from 20 to 60 millimeters of mercury, cerebral blood flow decreases, and everything works on a principle of vasodilatory cascade is increasing ICP, and vasoconstrictory cascade is decreasing intracranial pressure. Transitional period of rise, acutely raised intracranial pressure. Second component, as you remember, that was related to venous outflow. If venous outflow is altered, for example, here increase in sagittal sinus pressure, we see rise in intracranial pressure. This example is taken from patients with idiopathic intracranial hypertension, where there is a strong coupling between ICP and pressure in sagittal sinus. Therefore, this works as a closed loop, and we really cannot say what's chicken and what's egg. Another example, this is a problem with CSF circulation, so-called external hydrocephalus, where intracranial pressure following brain injury or subarachnoid hemorrhage is elevated. Ventricles are not large. We cannot see large ventricles, but we can see collection of cerebrospinal fluid in subarachnoid space. This is hydrocephalus, this external hydrocephalus is related to inability to absorb cerebrospinal fluid from subarachnoid space back to sagittal sinus blood. And finally, volumetric changes in brain tissue, which produce refractory intracranial hypertension. This produces very fast and very deep rise, but not like in plateau wave, not of the transitional manner or character, but really lasting intracranial hypertension, which produce decrease in cerebral perfusion pressure, decrease in cerebral blood flow, ischemia, and brain death. So we have all our four components. Now we need to think about how can we measure intracranial pressure. Nowadays, we are using intraparenchymal probes, but really definition of intracranial pressure is associated with measurement of cerebrospinal fluid pressure in ventricles. This is not very popular nowadays because this methodology had to apply external transducer, and this external transducer over a longer period of time was inevitably the source of possible infection. Nowadays, intraparenchymal transducers are really in use, and we have several types of such transducers: American, French, German. All are very popular. Important consequences of using intraparenchymal transducer instead of measurement of the pressure in CSF, cerebrospinal fluid, is the possibility of pressure gradients. This is example of intracranial pressure measurement using intraparenchymal transducers in two hemispheres in patients with midline shift. Sometimes we see very good convergence of two pressures, plus minus some kind of the calibration error, but this is understandable. But sometimes we see huge divergence between intracranial pressure in intraparenchymal measured with intraparenchymal probe between left and right hemisphere. Therefore, there is natural question. This difference is around 15 millimeter of mercury. What is a real intracranial pressure in this patient? Is it 30 millimeter of mercury or is it 17 millimeter of mercury? You know, 30 millimeter of mercury is really elevated intracranial pressure, mandating very aggressive treatment. 17 is normal intracranial pressure following traumatic brain injury. Therefore, there is a great need of measurement of intracranial pressure non-invasively. There are methodologies using transcranial Doppler ultrasonography. There are methodologies using the echo Doppler measurement of the optic nerve sheath diameter. Both are giving the possibility of monitoring of intracranial pressure. Here you can see unstable intracranial pressure. Red line shows the estimation using transcranial Doppler. And this reflects dynamics of intracranial pressure quite accurately. Optic nerve sheath diameter gives us static measurement of ICP. And the error is plus minus 8 millimeter of mercury. This is 95% confidence limit. Then, if we have the possibility to measure intracranial pressure invasively, we can always think whether measurement of the trend of ICP, like here, this is a history of the patients, which has been admitted at the beginning of my staying in Cambridge with around 20 millimeter of mercury beginning pressure, then pressure stabilized second day after head injury, and then it increased to the very high value on day 4, and inevitably patients died. Here we see increase in the dynamics of change of intracranial pressure with more and more frequent waves of ICP, ups and downs. And there is an open question whether, if we see this period of time and this period of time, can we really predict what's going on here on day 4. With this, we say normal ICP dynamics, almost normal ICP values, everything is okay. With this, we can say dynamics is increasing. That will produce probably in the near future, if ICP is not treated, real crisis. And it did. So therefore, it's important to see a little bit around and speak about a little bit of the dynamics of intracranial pressure. Patterns. Patterns, our observations. At the beginning of everything in science, we have observations. Then if our observations are repeatable, we can think about the statistics, writing the rules, writing the papers, and sending them to scientific journals. First pattern, ICP is stable, arterial blood pressure is stable. ICP is elevated about 20 millimeter of mercury. The stable elevated ICP is very, very commonly seen first things following head injury. Changes in ICP may be produced by changes in arterial blood pressure, like here. Any compensated change in arterial blood pressure and fast, it may be very, very high, produces change in intracranial pressure. No matter whether patients got a working or not working autoregulation. Changes in ICP then related to changes in cerebral blood flow. These are, I call them metabolic waves of ICP. Here we see rise of ICP from 15 to 45 millimeter of mercury associated with decrease in cerebral perfusion pressure, associated with increase in cerebral blood flow and increase in jugular valve oxygenation, showing that this is increase in cerebral blood flow and increase in cerebral blood volume producing such a profound deep increase in intracranial pressure. And finally, again, refractory intracranial hypertension. ICP over 4 hours, following admission of the patients increased to 100 millimeter of mercury that produced a Cushing response, decrease in cerebral perfusion pressure, and brain death. Plateau waves of ICP can be seen quite frequently, but not in all patients, approximately in 20% of the patients. These are vasodilatatory events producing increase in cerebral blood volume and increase in intracranial pressure, associated with decrease in cerebral perfusion pressure. Look at this, this is profound, decrease in CPP down to 40 millimeter of mercury. If we are lucky and monitor something else, like here, brain tissue oxygenation, we can see decreases in brain tissue oxygenation, showing that these waves of intracranial pressure and valleys of cerebral perfusion pressure are really ischemic events for the brain. Plateau waves are usually not that much danger unless they are very long. Here is an example showing that intracranial pressure was stable and little bit elevated following traumatic brain injury. And then we have the period of plateau waves, first, second, third, fourth, fifth, and every plateau wave terminated spontaneously. And unfortunately, seventh wave didn't terminate spontaneously and patient died. Long plateau waves are really very dangerous, and we need to intervene when we see elevations of ICP of plateau wave character longer than 30 minutes. Other waves of intracranial pressure, B waves of the period of 1 minute or 2 minutes, these are lower than 1 minute. Waves of the period shorter than few seconds, these are respiratory wave, and the waves synchronous with our heart variability. These are pulse waveform of intracranial pressure. All of them got its important physiological meaning and can carry information about brain homeostasis. First of all, B waves of intracranial pressure. We can see them here. This is a patient suffering from hydrocephalus, where we measure cerebrospinal fluid pressure and applied infusion to see what is circulation of cerebrospinal fluid, with this 1 minute period increasing its magnitude. If we look at the NIROS recording from the same patients, we can see that these waves of intracranial pressure are really synchronous. They are in phase with changes of desoxygenated hemoglobin. Therefore, these waves are related to cerebral blood volume. The waves following traumatic brain injury are related to the outcome. Very interestingly, in patients with bad outcome, these are severe disability patients, patients who died, patients with moderate disability, the magnitude, average magnitude of slow waves is decreasing with a worse outcome. Pulse amplitude of intracranial pressure is very important wave, and there is a lot of information included in this waveform. It's periodic. The frequency is equal to the frequency of heart rate. And very specifically, this is very early illustration from Professor Marmarou, Avezat, and Eidhoven, 1984, Professor Marmarou in 1973, showing that with increasing mean intracranial pressure, amplitude of pulse waveform tends to increase because the relationship between pressure and the volume, this is intracranial pressure, this is the volume of cerebrospinal fluid space, is exponential. This can be observed during for example, controlled elevation of intracranial pressure. During infusion test, we control ICP to see, to challenge the system, what is resistance to CSF outflow, and then we can measure also pulse amplitude. Relationship between amplitude and pressure is linear above certain pressure called optimal intracranial pressure. Below this is constant. And this can be explained by pressure volume curve. Below pressure optimal, the curve is really not a curve. This is a linear relationship between volume and the pressure. Above starts to be exponential. Here, pulse amplitude is constant, and here, pulse amplitude of intracranial pressure increases with mean intracranial pressure. If we calculate correlation coefficient between amplitude and pressure, this is so-called RAP coefficient, we can see that RAP here is 0. It's associated with a good compensatory reserve. And here RAP is equal to +1 because pulse amplitude increases with mean intracranial pressure. Therefore, this RAP coefficient may be quite good to recognize between good compensatory reserve and poor compensatory reserve. But there is a third zone of this pressure volume curve. This is where we reach so-called critical intracranial pressure, above which arterial bed starts to collapse. The curve deflects to the right, and here we see secondary decrease in the pulse amplitude of intracranial pressure. Our RAP coefficient reaches negative values. So this is RAP 0, good compensatory reserve, RAP 1, poor compensatory reserve, RAP negative. This is deranged cerebrovascular reactivity. And we know that we are working above critical level of intracranial pressure. And this is clinical recording of such an event, ICP increasing to very high values. Patients die because of refractory intracranial hypertension, but pulse amplitude was increasing with mean intracranial pressure until it reached certain break point and it starts to decrease. RAP goes to negative value. If we plot amplitude pressure relationship, we can see increasing in amplitude with mean intracranial pressure, then upper break point, and then decrease in the pulse amplitude with RAP negative. But RAP is very important and interesting and useful in monitoring pressure volume compensatory reserve in traumatic brain injury. RAP close to +1, once again, it's a poor compensatory reserve. We know that we are continuously working on the exponential part of pressure volume curve. Here, brain edema is decreasing. RAP, even if ICP stays a little bit elevated, about 20 millimeter of mercury, goes to 0. It means that the trouble is over. A little bit about cerebral regulation. Cerebral regulation is very important to keep brain happy, as you can see. And looking at the changes in arterial blood pressure and ICP may produce informal, important information about changes in cerebral regulation during critical care of the patients following traumatic brain injury. Slow waves of ABP and intracranial pressure can be detected always with a precise computer method, and negative correlation between slow waves of ABP and ICP, we calculate and call these correlation coefficients PRX, pressure reactivity index. Negative value shows good working autoregulation, positive passive transmission between slow waves of ICP and ABP to ICP indicates poor cerebral autoregulation. That has been proven by our friend Ken Brady, that crossing autoregulatory threshold where we plot cerebral blood flow versus cerebral perfusion pressure. This is experimental data. Crossing the lower limit of autoregulation is associated with increasing pressure activity index. And this gives us possibility of looking at pressure activity index to predict lower limit of autoregulation with area under the curve of the TEC 0.9. So this is very prestigious value. Pressure activity index is associated with outcome following traumatic brain injury, and if pressure activity index is negative or around 0, mortality rate stays on the good side, lower than 20%. But when pressure activity index increases above 0.3, at this point, mortality rate tends to increase to 70–80% right here. Lutz Steiner, our PhD student working with us in Cambridge, now he's professor of anesthesiology in Basel, in Switzerland, proposed the correlating cerebral perfusion pressure with pressure activity index, and he found that this has got the U-shaped curve. It means that for low cerebral perfusion pressure, autoregulation is not good. For high cerebral perfusion pressure, autoregulation also is not good. Here we have ischemia, here we have probably hyperemia, and somewhere in between ischemia and hyperemia, we see optimal cerebral autoregulation. He called it optimal cerebral perfusion pressure, and he showed that when the distance between real cerebral perfusion pressure and optimal cerebral perfusion pressure is lower, the outcome is much, much better than if it's on greater values. Peter Chmielewski, who is main author of ICM Plus software, found that it is possible by generally plotting PRX as a moving coefficient versus cerebral perfusion pressure, find this U-shaped curve and follow optimal cerebral perfusion pressure almost continuously. And that can be done, and therefore we can compare real cerebral perfusion pressure with the target, with optimal cerebral perfusion pressure, and manage the patients in a state which will be the best approximation of his optimal cerebral perfusion pressure. It means the state where cerebral autoregulation is working best. Marcel Arias, doing studies in Cambridge on our material, showed that if difference between CPP optimal and cerebral perfusion pressure actual is negative, this is associated with increased mortality rate. Where CPP is higher than CPP optimal, this is associated with increased severe disability. If we work around cerebral perfusion pressure optimal, the rate of favorable outcome is maximized. These are these 2 points. We just finished 1 year ago, first multi-center study about CPP optimal guided therapy, Cogitate, which showed and illustrated that following cerebral perfusion pressure optimal given by the computer, it's both safe and feasible, which opens the door to outcome-oriented clinical trial, which will start, I hope, quite soon. So messages to take home. ICP, I hope you believe, is more than a number. Pulse waveform of ICP helps to understand compensatory reserve. Pressure activity index can be derived from simple analysis of ABP and intracranial pressure. And there is a strong association with outcome, between outcome and PRX, and the detection of optimal cerebral perfusion pressure, and also optimal arterial blood pressure, and also critical intracranial pressure is possible. promising preparatory results not only in traumatic brain injury. I didn't show this to you because of the restrictions this time, but also in subarachnoid hemorrhage. We need a proper outcome-oriented randomized control trial. And at the end, many thanks to my friends and colleagues and collaborators from Brain Physics Laboratory. Thank you very much.
Dr. Marek, thank you very much for a very enthusiastic talk and very important data presented in this session. There is a couple of questions, but I would like to summarize one of them that probably would give us discussion for many hours. But do you believe that the ICP or the ICC, I mean the intracranial pressure or intracranial compliance, will be as known as use it as arterial pressure? The importance for having this information for patient, and if yes, when do you think it will happen?
Soon. I think that it happens as we speak, because the traumatic brain injury is a main killer of the younger person in our society, and because this affects the younger persons, it produces a great burden to the society to care and everything. Therefore, intracranial pressure, which I try to show being so crucial in terms of the surviving secondary brain injury, I think that this is fundamental monitoring modality, which is obviously associated with arterial blood pressure. This is why we speak about cerebral perfusion pressure, about control of cerebral perfusion pressure, about optimal cerebral perfusion pressure. Therefore, from the point of view of the treatment of traumatic brain injury, we are with traumatic brain injury. We have the war in Europe now. It's a great problem how to treat these patients.
Yeah. Okay, and if we don't have or if we cannot do the intracranial invasive intracranial pressure measurement, would you think that the waveform, the morphology of the intracranial pressure measured by non-invasive would tell us about how brain is perfused or not? How's your comment about that?
Yes, we started non-invasive monitoring, and in those cases, because I work in a busy hospital where there is a big neurocritical care unit. In neurocritical care unit, if you have critically ill patients, there is no question whether to monitor intracranial pressure or not to monitor. You do this, but if you have the patients in whom you cannot monitor, for example, with a liver failure, with coagulopathy, you need to use something to control management of these patients. And this is non-invasive intracranial pressure. We have, and we already described, number of patients in whom ICP-oriented therapy has been conducted using non-invasive methodologies.
Okay, very good. I think we have to move for another presentation. Dr. Marek, I greatly appreciate your timing with us this afternoon, and we hope to see you next time. And
thank you.
Wish you have luck in all your research. Many thanks for you.
Thank you.
Thank you.